Today we're going to start with acids and bases. Okay. And the first thing we're going to look at is the Bronsted-Lowry theory of acids and bases. Okay. The Bronsted-Lowry theory of acids and bases. Okay. Now, according to the Bronsted-Lowry theory, okay, how do we define an acid? So, according to the Bronsted-Lowry theory, okay, an acid is a proton donor. Okay, it is a proton donor. Whereas a base is a proton acceptor. So this is really the theory we study in depth in our syllabus, okay? But the way we define acids, or the way we define bases is basically something known as the Bronsted-Lowry theory. Okay, these guys said, you know what? An acid is what we call a proton donor. So a Bronsted-Lowry acid is a proton donor, right? And a Bronsted-Lowry base is a proton acceptor. So now let's say, for example, that I had ethanoic acid, right? And it was dissolved in water, right? And what we ended up making was CH3, CO2 minus, and H3O plus. Okay. This equation in a simplified form, it can be written as this. Okay? In a simplified form, it can be written as this. However, H plus ions in aqueous solution, okay, H plus ions actually exist as H3O plus ions. So like, you know, for example, when this acid loses its proton, right, that H plus ion actually combines with the water molecule to form H3O plus ions. So we accept this equation as well, right? This is the simplified version, but in actual aqueous solution, right, H3O plus ions are basically your H plus ions. Okay, the H plus ions actually combine with the water molecule to form H3O plus ions. So this is a simplified expression, whereas this is the actual species found in aqueous solution. This is known as the hydronium ion. This is known as the hydronium ion. So again, if we wanted to know the concentration of H plus in aqueous solution, we can simply find the concentration of H3O plus ions. Okay, as I said, however many H plus ions this acid is producing, right, that's going to be the number or the amount of H3O plus ions that we have in aqueous solution. So now if you look at this equation, right, what's the acid and what's the base? If you look at this equation, right, ethanoic acid is donating a proton and water is accepting a proton. So we can say that ethanoic acid is the acid, right, and water is the base, right. Ethanoic acid is losing a proton, it's donating a proton, and water is accepting a proton. So this is the base. More specifically, this is a Bronsted-Lowry acid, right? Because that's how we define acids according to the Bronsted-Lowry theory. The Bronsted-Lowry acid because it's a proton donor. This is a Bronsted-Lowry base because it's a proton acceptor. If you look at the reverse reaction, right, which of them is the acid and which is the base? So hydronium ion here is the acid, right, and the ethanoate ion is the base. The ethanoate ion is the base. Again, if you look at the reverse reaction, right, if you look at the backward reaction, when H3O plus donates a proton, right, to the ethanoate ion, so it donates a proton to form H2O, and this guy accepts a proton to form ethanoic acid. So if we look at the backward reaction, this is the acid and this is the base. Okay. Now, ethanoic acid and the ethanoate ion are known as a conjugate acid-base pair. Okay. A conjugate acid-base pair. Okay. What a conjugate acid-base pair is basically, right? What you have is when an acid loses a proton, it forms its conjugate base. When an acid loses a proton, it forms its conjugate base. And when a base gains a proton, it forms its conjugate acid. Okay. So H2O and H3O plus are also a H2O and H3O plus are also a conjugate acid base pair. So what that means is, right, if you look at ethanoic acid, right, when ethanoic acid loses a proton, right, ethanoic acid is an acid in this particular reaction. When it loses a proton, it forms its conjugate base, that is the ethanoate ion. Similarly, we can also say that when the ethanoate ion gains a proton, it forms ethanoic acid. So we can say that the ethanoate ion is the conjugate base of ethanoic acid, and ethanoic acid is the conjugate acid of the ethanoate ion. Similarly, we can say that if H2O is a base here, the conjugate acid of H2O is the hydronium ion, right? Because when H2O gains a proton, it forms the hydronium ion. So this is the base, it's accepting a proton, and when it accepts a proton, it forms its conjugate acid. Similarly, we can say that water is the conjugate base of the hydronium ion. When the hydronium ion loses a proton, it forms its conjugate base. Okay. So what we can say is that if we have like, let's say, a conjugate acid, okay, when that conjugate acid loses a proton, it forms its conjugate base. Okay, and similarly, when that conjugate base gains a proton, it forms its conjugate acid. Okay. So this is what we mean by a conjugate acid base pair. H2 and H3O plus are a conjugate acid base pair, right? If H2 gains a proton, it forms hydronium ions. If hydronium ions lose a proton, they form H2O. And same thing with ethanoic acid and ethanoate ion. When ethanoic acid loses a proton, it forms its conjugate base, which is the ethanoate ion. And when the ethanoate ion gains a proton, it forms its conjugate acid, which is the ethanoic acid. All right, so the next example that we're going to look at is between ammonia and water. Right? And here, right, ammonia forms ammonium ions, and water loses a proton to form hydroxide ions. So in this case, ammonia is the base and water is the acid. And for the reverse reaction, right, ammonia is accepting a proton from water, so water is an acid, it's a proton donor, ammonia is a proton acceptor. And for the reverse reaction, right, ammonium and hydroxide are forming ammonia and water, so we can say that ammonium is an acid, right, it's a proton donor, and it donates a proton to hydroxide, which when it accepts a proton, right, it forms H2O. So again, here we can say that ammonia and ammonium ions are conjugate acid base pair. Okay, they are a conjugate. Again, the word conjugate literally just means a couple or connected. Okay, so they're essentially related to each other. Okay, so conjugate acid base pair. Right? And similarly, we can say that water and hydroxide are also a conjugate acid base pair. Okay. So we can say that the ammonium ion is the conjugate acid of ammonia. When ammonia gains a proton, it forms the ammonium ion. And we can also say that ammonia is the conjugate base of the ammonium ion. When ammonium ions lose protons, they form ammonia. Okay. Similarly, the hydroxide ion is the conjugate base of water, and water is the conjugate acid of hydroxide. So now we're going to look at strengths of acids and bases. Okay, we're going to look at strengths of acids and bases. So when we say that we have a strong acid or a strong base, what do we mean? A strong acid or a strong base? So a strong acid or a strong base, okay, ionizes completely, okay, in solution. Ionizes, or you can say dissociates completely in solution. Okay. So when we talk about acid strength, okay, or a strength of a base, we're not talking about the concentration or the solubility. We're simply talking about how much it ionizes or dissociates in solution. So I'll give you an example. For example, right, a simple example would be of HCl, right? HCl in aqueous solution, right? We form H3O plus and Cl minus, right? And again, the chloride ion is the conjugate base of HCl, and HCl is the conjugate acid of chloride. Similarly, H3O plus is the conjugate acid of H2O, and H2O is the conjugate base of H3O plus. And we write this, as I said, we write this equation in a simplified form as HCl dissociates or ionizes completely to form H plus and Cl minus. So again, what we're saying here is, for example, if I dissolve like a million units of HCl, 999,999 would dissociate. A very, like, you'd have 99.999% dissociation, or a very large percentage of dissociation. What we can say is that whatever dissolved, ionized or dissociated completely. Okay, and therefore we call that a strong acid. Now consider the example of something like magnesium hydroxide, right? Now magnesium hydroxide is considered a strong base. It ionizes completely in solution to form magnesium ions and hydroxide ions. However, the pH for this solution is roughly 8. That's a very low pH for a strong base, right? Why is that the case? So this pH is affected by the solubility. Magnesium hydroxide is not very soluble in water. That does not necessarily make it a weak base. So for example, right, if you look at magnesium hydroxide, right, if we look at this example, right, if let's say I have a solid sample of magnesium hydroxide, right, now only a small fraction will actually dissolve, right? The majority of it won't dissolve, because it's partially soluble, so a small amount will dissolve. But whatever does dissolve will ionize completely. So for example, as just a simplification, if I had like 1 mole of this, maybe only 0.1 moles will dissolve, right? But whatever does dissolve, jo kuch dissolve karega, whatever does dissolve will ionize completely. Okay? So something can have low solubility but still be a strong base, right? So it won't make a very concentrated solution because it's fairly insoluble, right? So only a little bit of it will dissolve, but whatever does dissolve ionizes completely. Okay, so therefore we call it a strong base. Even though it doesn't have a very high pH, the pH is for this base is relatively low because it's relatively insoluble, but it is still a strong base. Okay, because whatever does dissolve ionizes completely. Now when we say that something is a weak acid or a weak base, right, what that means is that it only partially ionizes or dissociates in solution. Okay, only partially ionizes or dissociates in solution. So an example of a weak acid would be ethanoic acid, right? And we'll just look at the simplified form of this equation, right? Now ethanoic acid is a classic example of a weak acid that's very soluble in water, right? It can form hydrogen bonds with water. We studied this previously. We know that ethanoic acid is very soluble in water, right? So a very large amount will dissolve in water, but of that a very small fraction will ionize. So for example, if I dissolved 1 mole, only maybe 0.02 moles or 0.03 moles, only 2 to 3% of the molecules will actually end up forming H plus ions. Okay, जो कुछ dissolve करेगा, मिसाल के तौर पे, for example, अगर 1 mole ने dissolve किया, if I dissolve 1 mole, right, a small fraction of those, maybe 2% or 3% of those molecules will actually end up forming ions. So ethanoic acid is an example of something that's very soluble, but whatever does dissolve, only a small fraction of those molecules actually end up forming H plus ions. Okay. Same thing with ammonia, right? Ammonia is a weak base. It's very soluble in water because it can form hydrogen bonds with water, but a small fraction of what dissolves, a very small percentage of the molecules that dissolve actually end up accepting a proton. Okay, so a very small fraction of them actually ionize to form ammonium ions and hydroxide ions. Okay, so here HCl is an example of a strong acid, right? Magnesium hydroxide is a strong base, right? Ethanoic acid is an example of a weak acid, and ammonia is an example of a weak base. So here then we can say over here that the acid strength, okay, depends on the degree of ionization or dissociation in solution. In other words, once it has dissolved, what fraction of it actually ionizes in solution. And strength is not the same as, okay, solubility or concentration. Okay, solubility and concentration do not determine strength. Okay, it's only the degree of ionization. All right, so the last thing that we want to talk about is that the stronger an acid, okay, the stronger an acid, the weaker its conjugate base. Okay, so the stronger an acid, okay, the weaker its conjugate base. Stronger acid means weaker conjugate base. And vice versa, right? Weaker acid means stronger conjugate base. So for example, right, if we were comparing something like HCl and ethanoic acid, right? And here we have ethanoic acid, CH3CO2H, forming CH3CO2 minus and H plus, right? We know that HCl is a strong acid, which means that the chloride ion is a very weak conjugate base, right? So if we look at these two acids, HCl is the stronger acid. Okay. It's the stronger acid. So that means that the forward reaction, right, it pretty much almost completely ionizes, which means that the backward reaction is, non-existent, which means that, so what that means is essentially because the backward reaction is, like pretty much non-existent, we can say that chloride has a very, very small tendency to accept protons. It pretty much doesn't accept protons to form HCl. There's a like one-way traffic, right? So we can say that the chloride ion is a very weak conjugate base. Okay, this is a very weak conjugate base. Weaker conjugate base. On the other hand, if you look at ethanoic acid and the ethanoate ion, right? Ethanoic acid is the weaker acid, right? Of the two, between HCl and ethanoic acid, which means that the forward reaction isn't as favored, which also means that the backward reaction in this case is more favored than in the first case. So that means that the ethanoate ion will more readily accept protons than the chloride ion would. So we can say that this is a stronger conjugate base than the chloride ion.